Beautiful. Yeah, sorry about the delay. So first of all, I'm very grateful to the organizers for giving me a chance to talk at this great meeting. It's also my first visit to India, and I'm very excited both by the country and by the people. It's really great. So indeed, I want to talk about transport in strongly correlated metals, and I'll show you how bad metals turn good, and basically how this can be seen in spectroscopic measures. So first of all, these are the minds behind this work. Zhou Yudeng, which is now a postdoc with Gabi Kotliar at Rutgers. Yernem Lavlier, who is at Ljubljana University, and Rok Žitko, who's also there, and Antoine Georges. I think he doesn't need an introduction. So as we've seen this morning in the talk of Antoine, and also, for example, yesterday with André-Marie Tremblay, strongly correlated systems, they do, as Antoine says, they do big things that show up in their phase diagrams, which are rich. Think of the phase diagram of cuprates. They're very rich phase diagrams, and of course, this rich physics also appears in, if you want, more direct measures, namely in transport. So bad metallic behavior often is a signature of having a strongly correlated system. Often these strongly correlated systems, they have resistivities which are above something which is the Mottio-Feregel limit, which I'll talk about, but which is a signature of bad metallicity. Also, if they show Fermi liquid behavior, this happens at rather low temperatures if there is Fermi liquid behavior at all. Okay, so resistivity is something which is maybe quite simple to measure, but when it comes to understanding really what it is, this is a totally different story, and as far as theory is concerned, it's quite a bit of a challenge. So let me go to this Mottio-Feregel limit. So if I want to describe transport or current in a system based on a quasiparticle description, well, this only can make sense if the mean free path of these quasiparticles is longer than the Fermi wavelengths. André-Marie Tremblay already discussed this yesterday, but of course if this mean free path starts to be shorter than these Fermi wavelengths, you cannot describe transport with quasiparticles. So if, for example, I start with the Drude formula for, here I took the example of a simple quasi 2D geometry. That's the expression for the conductivity. Basically that's the interplane distance, the Fermi momentum here, and the average, the mean free path here. So the limit where things stop making sense is more or less when this condition here is fulfilled, that Kf or L, the mean free path, is shorter than the Fermi wavelengths. So setting this limit and plugging this in here sets sort of a critical conductivity, which makes sense when I describe the system with quasiparticles, or it sets, if you want, a maximum resistivity above which you don't expect the system to go, at least if you describe it with quasiparticles. So this critical resistivity is the Mottio-Feregel limit, and this is an order of magnitude of this quantity. Okay, so let me here show a prototypical bad metal. So I took the example of strontium-2, Roteneo-4. This is here the the plot of the resistivity versus temperature. And these different arrows here are slightly different estimates of this maximum resistivity, the Mottio-Feregel limit. It doesn't really matter. What matters is that in any case, this resistivity goes way above this limit. So clearly, the system has resistivities which are way bigger than the rho of Mottio-Feregel. So this is a signature of bad metallicity. And actually, before this example, I mean, there's also this kind of behavior, for example, in cuprates. And it was at least suggested that seeing this bad metallicity is maybe the signal, or can only occur if the ground state of my system is something exotic. I think this idea has been around a little bit, but here clearly this is an example where this is not true. Namely, if I go down to very low temperature and I zoom here, and I again look at the conductivity, I look at this curve here as a function of temperature, actually I find back a normal Fermi liquid T-square behavior, but this happens only at very low temperature. Okay, but nevertheless, my ground state seems to be a very well behaved Fermi liquid. The only thing is the two scales are very different. So you see this is below 20 Kelvin, and this happens, the Monte-Carlo limit is here somewhere around 600 Kelvin. So these are very different scales. So there are other examples. For example, this material who has the same kind of behavior with, again, Fermi liquid behavior seen only below 2 Kelvin, and a Monte-Carlo limit, which is a few times 100 Kelvin. So you see, again, two very different scales. Again, one can ask the question if cuprates also belong to these examples. They definitely have resistivities larger than a Monte-Carlo limit. What about their low temperature state? There are quantum oscillations, which suggest that maybe it is a Fermi liquid. So I think these questions are very timely about what this resistivity really does here at low temperature. Okay, so basically the key questions I'm trying to address here is how to describe generally transport in these strongly correlated systems. And as I told you, this Fermi liquid temperature and the Monte-Carlo temperature are two very distinct scales. So what is this T Fermi liquid, and what happens when I go above T Fermi liquid? Do I still have quasiparticles? How do I describe them? What happens all the way to this other energy scale, the Monte-Carlo temperature? What happens in between? How can I describe transport in this regime? And what happens then at this Monte-Carlo limit and above? How can I describe the system there? So that's basically the questions I want to try to address here. So in order to indeed address these questions, the simplest model, which also Antoine talked about this morning, is our model playground, the Hubbard model. Here we took it in its simplest single band version, and we'll study it by doping it with holes. And we use DMFT to study this system. Okay, so there will be extensive introductions about DMFT for students next week. So I don't remind it here, but I'll show nevertheless how the conductivity, for example, is computed within DMFT. So here are just the typical parameters that we took. There are parameters that are such that the system is actually in a strongly correlated regime. Now, probably the reason why this kind of work hasn't been done maybe earlier is that actually computing transport is quite a bit of a challenge numerically, especially over the full range of temperature. So you want to find methods that are able to describe very nicely quite low temperatures, but also can go to reasonably high temperatures. So we took all the efforts of using the numerical randomization group, here using the code of Roch Gitco, which is actually open source on this website, which is the Ljubljana code, together with CT, QMC methods, both in their hybridization and interaction expansion versions. This is something we'll discuss next week. And an analytical continuation, which is done with PADE approximants. And this has been done with the TRIX package, which is also an open source package that you can get here, which we develop between Saclay and École Polytechnique. So to get more info, you can look at this review by Emmanuel Goul and collaborators. So using those tools, we could really study the full range of temperatures. And just to mention, this is not the very first DMFT work that addresses similar questions. So I've mentioned a couple of them here. There's actually also work by Thomas Pruschke, who's here on this subject. So just to give you a little an idea, a benchmark about this is maybe more for experts, but I think it's worth looking at it for a second. So typically the quantity we're trying to continue analytically on the real axis is the self-energy, to get the self-energy of the problem on the real axis. And this is what we get using these two methods. It's always the same curve, except we're zooming in at lower and lower energies. And the two curves are what we obtain by NRG, and in green using Monte Carlo plus PADE approximant. So you see it's quite nice that these curves match quite nicely together all the way down to really low frequencies. So this requires a lot of numerical effort. But I think having two methods also is a way to actually benchmark that we're not doing too crazy things. Okay, so just here some formalism, but this is just going to be this slide. So within DMFT, like Antoine said this morning, basically the idea is you start from your model on a lattice, the Hubbard model on a lattice, and you map it on a simpler, but still not so easy, model of a quantum impurity embedded in a bath, and you solve this self-consistently. The price to pay in this approximation basically is that you still have the local dynamics of your problem, which basically means that you still have a self-energy for your problem, which is dependent on frequency, but you lose its K dependence. Okay, you have no information about spatial correlations. So because of this, an expression for the spectral function is something like this, which is almost the usual formula, except there is no K dependence here. Now within DMFT, and this is quite nice for a theorist, it turns out that vertex corrections vanish, which means that when you go use your Kubo formulas to compute the conductivity, actually you're just left with this expression, which is in a sense not too complex, an integral over frequencies, derivative of the Fermi function, and your spectral functions here, and here the Fermi velocity. Sure, please. Yeah, so for more involved people, this is DMFT done on a beta lattice. Okay, so let me now switch to the results. So the main result is that we find three regions of transport. So this is a plot as a function of temperature here and hole doping. So what we find is that at very low temperature, there is a region where the system is definitely a Fermi liquid with everything you expect from a Fermi liquid. I'll show this in more details. And this happens below a temperature which grows linearly with doping, but with a very small slope. So this is actually a very small temperature. This line here is the line which shows where the resistivity goes above the Mottio-Ferregel limit. And above this, we definitely have a bad metal with essentially no quasiparticles there. So there's no quasiparticles living in there. But between these two temperatures, there's an extended region here where we still have a metal with quasiparticles, which are sort of resilient quasiparticles, which don't behave as standard Fermi liquid quasiparticles, but still, which from a pragmatic point of view, are definitely quasiparticles. Oh, so U is 4D in that case. So let me go through these different regions a little more in detail. So this is typically the resistivity curves we obtain here for different doping levels as a function of temperature here. And this is the resistivity normalized by the Mottio-Ferregel limit here. So these curves, they basically start at very low temperature as T squared. These are the curves, I mean, it's an inset of, at low temperature, it's scaled with the doping, so the curves pretty much collapse, and this T squared behavior resists up to this quite low temperature here. So this is what you see here. Then it has a sort of a first linear behavior, a kink to a second linear behavior, and above the Mottio-Ferregel limit, we have this linear resistivity, okay? So that's the generic look of the resistivity versus temperature. So if I really go down to low temperatures and look at this Fermi liquid regime, so as I said, first of all, the temperature is really small. It's proportional to the doping, but with a really small prefactor, much smaller than, if you want, the Brinkmann-Rice scale. And actually, the way we did to determine this Fermi liquid temperature precisely, I mean, it's basically to look, for example, at Z divided by Z taken at 0 temperature. So these curves, so we look at this as a function of temperature, so all the curves, they collapse, and what you expect for a Fermi liquid is that Z, which is the quasiparticle peak, sorry, I should have mentioned, is independent of temperature. So you get something really flat, and where it deviates, this sort of sets this Fermi liquid scale. So here, this is all local, so we're doing DMFT, so the self-energy is purely local, so there's no K dependence for Z in that case, okay? So it's Z here, which doesn't have a K, because this is the DMFT self-energy here, okay? We can also look at the imaginary part of the self-energy, for which we expect something which goes like omega squared plus pi t squared, and again, things collapse quite nicely on this parabola at very low temperature, but as soon as we increase temperature, you see already on the positive frequency size, we very quickly lose the Fermi liquid behavior. So actually, as you see, this happens in a manner which is not symmetric, and I'll come back to that point more in details in the future, I mean, later on in the talk, okay? Good. It's normalized. So this curve is Z here is the Z that you obtain at low temperature. So it's not equal to 1. It's a correlated. How much? 0.2 in that case. Yeah, this is doping. Is it written? It's the doping is 0.2. Yeah. Oh yeah. Sorry. So yeah, indeed, it's more or less proportional to doping, and in that case, the doping is 0.2. This is the curve. Yeah, indeed, that works nicely with Gutzwiller. Okay, so let me describe now what happens as I increase a little the temperature here. So I was in the Fermi liquid, and now I increase the temperature, and I want to investigate here what happens in this intermediate region where I want to justify or show you that there are still quasiparticles. So let me first show this. This is a plot of the spectral function, so the local density of states, if you want, versus frequency. And so at low temperature, this is this black curve. You see a very evident structure here of the quasiparticle peak. But as I increase temperature, so already this blue curve is already here in this region, I still have a clear signature of a quasiparticle which is distinct from this lower Hubbard band. Same thing still for this maybe pink curve here. And eventually at higher temperatures, this quasiparticle peak merges into the lower Hubbard band. So to see this maybe more in details, I can also look at this. These are now plots of the spectral function, but AK of omega for different K points that are cross, if you want, the Fermi level. So you said low energy, I really see this quasiparticle peak crossing the Fermi level. And as I increase the temperature, here I'm in the resilient quasiparticle regime. I still have a very clear signature here of the quasiparticle peak crossing. And only at much higher temperature, eventually, this quasiparticle peak merges into the lower Hubbard band. One thing which I want to draw your attention to is that you see these quasiparticle peaks, they actually have a much larger amplitude on the positive frequency side than on the negative frequency side. So when you look at these plots, note that most of these quasiparticles seem to live actually more on the positive frequency side. Okay, I'll come back to this. All right, so let me try indeed to explain this, the fact that these quasiparticles seem to be stronger on the positive omega side. So this is now, like I showed.
Like saying that it's easier to remove an electron than to add one?
Yeah, I think you can, yeah, it is. Eventually, I mean, what it really means is, yes, transport is dominated by electrons, which is exactly what you're saying. Yeah, at very low time in the Fermi liquid.
Very low frequency, zero energy. Omega squared is no, but if there's a U that is involved. The average, the electron motion averages out the U effect. So, I mean, after all, when you say Gutzwiller factor, you're already making quasiparticle assumptions. You have full correlation inside.
Well, this is for the number.
It comes out.
Of course, at high energy, it's much easier to remove a particle and to add a particle. But this asymmetry, the point is that this particular asymmetry continues to have an influence down to very low energy scale. Immediately beyond Fermi liquid theory.
Yeah, exactly. So you don't need to be at a very high temperature to see this, and you'll see clear signatures of this, and for example, in the Seebeck coefficient. So exactly, still to try to make this point. So I've shown you earlier self-energy plots here, the omega squared behavior at very low frequency. I'm just showing this imaginary part of the self-energy on a wider scale here for different temperatures. And as you see, as I increase the temperature, I start from this Fermi liquid, and these curves are very asymmetric. And what's quite striking is that on the negative frequency side, this self-energy becomes quite big, while it sort of flattens here and remains small. Okay?
Critical temperature at which the self-energy value takes off from zero and starts going up. Is that the same?
Well, it never touches zero because it always goes as t squared. So it's but if you want, it's when it really deviates from the omega squared behavior. Okay. But so at these positive frequencies, these values are really low. So if you want, this has a small scattering on the positive frequency sides, and this is why we saw this big signal on the positive side with quasiparticles. So you can understand it also from this plot here. So these plots are, as a function of temperature, show the imaginary part of the self-energy at given frequencies here. So the black curve is, for example, the one you get exactly here at omega 0. What is above here are different curves for omega smaller than 0. So you see, as I increase temperature on the negative frequency side, this self-energy very quickly becomes very big. So I'm killing my negative frequency quasiparticles very quickly, while quite the opposite happens at positive frequencies, where as I increase the temperature, I still get values here which are really small.
I didn't quite understand. Is there a simple reason to understand what brings this asymmetry?
Yeah, well, yeah, I think the, actually, I'm coming back to this in a bit. So yeah, sure.
One question I have, in sigma doesn't depend on frequency very much on the
Yes, indeed.
Is it as if there's some static scatter?
Yeah, indeed. Yeah, I think that's correct. I mean, ultimately the reason I think is that there are not so many places to scatter against, because I'm doping my Hubbard band. Basically, I have a gap. So I'm left with not so many states in that region on positive frequency side. So ultimately, there's not much to scatter against, and this is why I think this is quite flat and remains pretty small. Okay, so still to make this point, these are plots of, again, A of K and omega. This is omega, and this is K if you want, this is omega here. And again, you see at low temperature, so this is my quasi-particle peak, which crosses the Fermi level, very visible here. But in all these cases, you see the signal is a lot stronger here on this positive frequency side. And this, again, goes in the direction of what, for example, Silke and also Antoine said this morning. It would really be interesting to be able to go see the dark side here of the Fermi surface, see what happens. And eventually, I mean, this band here exists up to quite high temperature, and it's only when I reach here somewhere, the Mottio-Ferregel temperature, that this quasi-particle peak merges into the lower Hubbard band, and here I have something which is completely incoherent. Okay, so let me show some signatures of this physics in the optical conductivity, for example. So this is the optical conductivity here as a function of frequency for different temperatures. So at very low temperature, what you see, I have this Ruder peak here. And actually, in the Fermi liquid regime, there's this little kink here, which is sort of a signal that I'm in the Fermi liquid regime. I think Antoine will have some more to say about this in his talk tomorrow. And then there's a second structure, a mid-infrared structure here. So then as I increase the temperature and go out of this Fermi liquid regime, well, I lose this little kink or foot-like structure here, but still get a quite clear Ruder peak, but which is not a Fermi liquid Ruder peak, so it doesn't really die as 1 over omega squared. And eventually, as I increase temperatures, it merges into this infrared structure, and I just have one big thing, which eventually evolves in something completely incoherent here. Okay? So now we see actually that up to that temperature here, this is the integrated optical conductivity here. We see that up to temperatures here, maybe this blue line here, essentially all the action as far as spectral wave transfer is concerned happens below this mid-infrared region here. And then as I go to higher temperatures, somewhere in the middle of my resilient quasi-particle regime, then spectral transfer happens on the whole scale here. This is what you can see here. Starting from some temperatures here, I start deviating in my mid-infrared, and I start having spectral wave transfer over a much wider energy scale. Okay, so let me say a word, so how we describe then transport in these different regimes. So the Fermi liquid regime is well understood, but in between these two regimes, I would like to understand how transport can be described. And it turns out that you can act quite nicely in the resilient quasi-particle regime, describe transport still using sort of a modified Drude formalism, but what basically drives the behavior of the conductivity is essentially the temperature dependence of the scattering rate. It's mainly encoded there. And only as you reach then the Mottio-Ferregel limit, you completely lose quasi-particles. You have a completely incoherent system. And then what drives the fact that the conductivity still increases with temperature is basically that you lose carriers. It's like you have rigid bands, and with increasing temperature, you basically lose carriers. And this is seen quite nicely by here a plot that is provided by Roque-Gitko. This is unpublished data, which shows that as you increase temperature, the scattering rate at some point stops increasing. So as you go to the Monte-Carlo limit, your scattering rate eventually saturates. So if the physics were just about scattering rates, the conductivity wouldn't go up. I mean, the resistivity wouldn't keep on increasing. So the reason it keeps on increasing is that you lose basically carriers in that regime. Okay, so well, we discussed this already. This is the place when I thought I wanted to discuss this particle Hall symmetry a little more. But like we said, I think the reason why this here is quite small is indeed that we basically have two Hubbard bands. We dope the lower Hubbard bands, and we have nothing in between, nothing to scatter against. And I think this is why this remains low and quite structure-less. So one can think about consequences of this asymmetry. And one place where the asymmetry has quite dramatic consequences is thermal power. So we computed here at the Seebeck coefficient. It's the black curve as a function of temperature. And the little correction here, this is just the Fermi liquid result. The main correction to this actually comes from the asymmetry of the self-energy at low frequencies. And you see there's quite a dramatic impact on the slope here, which is almost twice as big because of the asymmetry here. Now another consequence here that you can see is that most of this curve is actually on the negative, at least in this temperature regime here. A lot of the transport is dominated by the negative Seebeck, which means the transport is dominated by electrons. And this is exactly what I was trying to say earlier. The quasiparticle peak was big on this positive frequency side. So transport is really dominated by these resilient quasiparticles that sort of live on the electron-like side of the spectrum. And this is directly visible in this Seebeck coefficient. Yeah, so this is another surprising thing which I think calls for a little more understanding. But indeed, this is the entropy curve here, and it rises extremely quickly to very large values. Same thing if you want, this is the local susceptibility. So it really looks like this intermediate regime is can be described as sort of a two-fluid picture. I mean, it looks like there's coexistence with localized kind of moments that give rise to this large entropy and these resilient quasiparticles that drive the transport. So this is, you start from very high temperature, get the energy, compute it down, and get the derivative. What's that? Yes, yes, sorry, where am I? Yeah, which, no, actually, log 2 would be slightly higher. Oh, black dotted, yeah. Indeed, yeah. So it goes to the indeed isolation. The Fermi temperature, you mean for U0? Oof, I don't know in that case. Do you know?
What I'm wondering is, after some temperature, can you do like a purely classical thing? Yeah, but his delta is 0.1.
Well, this is 0.2 in that case.
We can calculate 0.8 electrons per unit cell.
You were asking after what point I sort of.
Yeah, I would think that's like something like half of the matrix. So just after that will be like you will be able to get this in classical description.
Well, that's a good question. I don't know above which temperature one can really describe the system as something purely classical. I'm not sure. I would suspect it's actually quite large temperatures. Yeah, but this is still quite big. I mean, on that scale, it's somewhere here. Yeah, but sure. Oh, yeah, in that regime, this might actually be sure. But you see, quite long before this, I have entropies which are quite big already. I mean, okay, so let me conclude at that stage. So I'm trying to convince you that there are two distinct energy scales. There's a Fermi liquid temperature, which is really small, a Monte-Carlo temperature, which is a lot larger. But between these two temperatures, there's still life for quasiparticles beyond Fermi liquid. There are resilient quasiparticles. They have small scattering rates on the positive frequency side, which has consequences for thermal power, for example. And there are signature in spectroscopy measurements, and probably Antoine will say more about these signatures tomorrow. And I think this kind of work is also useful in when think, for example, about cuprates in the quest for these low T states. Having bad metallic behavior doesn't mean that at low temperatures fancy things have to happen. So maybe these are this is good for cuprates as well. So with this, I'd like to thank you for your attention. And
during the talk, what happens as a function of u? If you go to, when you vary u, so for example, if you're at u equal to 1/10 of this, then you might be able to do some perturbative calculation, including the k effects and so on. And then how does this compare?
Well, the range of validity of a purely perturbative approach, I think you need really small u's. Yeah, so low U's, I don't know exactly what has been done already. Yeah, well, I don't know.
I think what they find is that there's a change in Fermi surface, so that's something we leave. Thanks. If I remember correctly, so Veljko Slatic did calculations based on second-order perturbation theory for the two-dimensional Hubbard model, and what he observed is that close to for small hole doping, you actually find a hole-like Fermi surface. So the change of topology for small doping, that's something you would never find in DMFT.
Sure.
So that's the only thing I can say here at that point.
Okay.
Maybe I can elaborate on this. So, in fact, this strong asymmetry is really developing in the large U limit, sufficiently large U. And it really comes from the fact that there is a complete separation of energy scales between the lower Hubbard band, which is rather close by in the mid-infrared range, and the upper Hubbard band, which is at infinity, if you want. So when you stick in an electron, it doesn't have much phase space to relax, and this is why there is this saturation of scattering rate. So one thing I want to emphasize is that recently Sriram Shastri, I don't know if he came and talked about this here, but he developed another approach called extremely correlated Fermi liquid, which we recently made detailed comparison in collaboration with Sriram, and all these features of low energy asymmetry and is completely common between ECFL and DMFT.
Yeah, at least if in that framework you really remain weak you do second order perturbation theory and look at the asymmetry of the self-energy, as I realized yesterday, it purely comes from the original asymmetry of the density of states. So in a purely weakly coupled system, it's going to be really small. So you need to open that gap to really have a big asymmetry.
So does it mean if I change the lattice to have a big effect? The whole thing was on Bethe lattice if I...
Well, I don't expect this to be very much dependent on this. I mean, it's dependent on the fact that you open a gap. So what the actual original density of states was, I think has no big influence. Of course, if you had something very specific where the original asymmetry for some reason was huge because you're sitting on a singularity, then of course you might see some effect on the self-energy even at perturbation level, sure.
In fact, in my talk tomorrow, if I get to there, I will show some very recent calculations that have to do with the real material, with strontium 2 ruthenium 4. So this is realistic DMFT, in which all this physics of this asymmetry is still there, is still present. And there has been high precision optical conductivity experiment by Dirk van der Marel's group that really revealed this effect, the existence of this resilient quasiparticle on the positive energy side. So I'll try to show this experimental data tomorrow.
Yeah, I just wanted for historical reasons. I mean, it's amazing that this has not been done till now.
That's right.
Because the method has been around for 20 years, and there are lots of calculations approximately of this kind.
That's absolutely. Well, maybe I can also say something on this. So indeed, you're right. I mean, in principle, this could have been done just a few years after the elaboration of limit. However, the fascinating transport requires extremely high accuracy solvers. So this is why we reconsider this, because even though the theory has been existing for 20 years, it was not possible to calculate any of the transport quantities with that level of accuracy at the time.
But there are calculations of resistivity, Prushke,
Yeah.
they have, and then
Yeah,
there are,
of course.
and then I think Kotliar, Gaby Kotliar had calculations of thermo power.
Yes, actually, at that point we had NCA and QMC based on Hirsch-Phi available. And as Antoine said, NCA has a problem at low temperatures, so we can't reach that very low region. And Hirsch-Phi QMC also has trouble if you go to very low temperatures. Now, an alternative would be NRG, but NRG has again problems if you really want to look at the Fermi liquid regime in that much detail. So you have shifts of self-energy which might not be exactly zero at low temperatures, or might even be on the positive energy side. And then extracting those high, very detailed things becomes extremely cumbersome. So Krish may talk about this. They try to involve on that, but especially very low temperatures, accessing very low temperatures transport, as Antoine said, is very, very cumbersome, and only possible recently due to this especially hybridization, expansion, and high accuracy Monte Carlo data at low temperatures.
In fact, you know, one can make your observation in a broader context. I mean, forgetting completely about DMFT, I find it rather surprising that the actual correct interpretation of the Monte-Carlo limit versus the Fermi liquid scale in the field of correlated electrons has been obscure for so many decades. Because when you think about it, so I think there's been a confusion about the nature of the Brinkman-Rice scale, you know, delta times bandwidth. This scale has absolutely nothing to do with Fermi liquid coherence. It appears in slave boson calculations as the condensation scale, but the correct interpretation is when quasiparticles appear, not when Fermi liquid sets in.
Right.
So this scale is actually the Monte-Carlo scale. Above that scale, there are no quasiparticles. Below that scale, there is quasiparticle. Fermi liquid is a different story. It happens at a much lower scale when all the phase space constraints become relevant and you get omega square. So that's the story. But this story could have been formulated in words, I don't know, a long time ago.
You know, I don't know this field, but I thought there was also a paper by Gaby Kotliar and so on, in which they calculate thermo power, or they said they had calculated thermo power.
Yeah, there's lots of work, but this notion that there is an intermediate regime very clearly defined, in which, you know, you have the Fermi liquid scale, the Monte-Carlo scale, and in between there are quasiparticles that survive, which would give resistivity which is not T square. And this business has not been really emphasized.
Any other questions? This asymmetry in the self-energy, I don't know if you have found this, but sometimes you can find even a sign change in the thermal power due to the asymmetry.
Yeah, sure. Principle, sure. If it's strong enough, well, you know this very well. Yeah, sure.
Okay, I'm afraid we have to go on to the next talk. Let's thank the speaker again.